Now we'll see the working of FM demodulation using PLL. So we are using the PLL IC 565. So before we start demodulating signal, first let us not give the FM signal. First verify whether we are getting the free running signal at pin number 5 and 6, because as you can see in the circuit diagram, pin number 5 and 6 are shorted. So at pin number 5 and 6, so we need to have, so as you can see here, so at pin number 4 and 5, so as these two are shorted, we are supposed to end up with a square wave at pin number 4 or 5. So that's what we are seeing here. So it was designed for a frequency of 100 kilohertz. So that was the carrier frequency of the FM demodulation circuit. So first let us verify what is the frequency of this one. So we can verify what is the frequency of this one, which was designed for 100 kilohertz. So once we are through with this square wave, next we need to first log this PLL to that VCO frequency. So we'll apply just the carrier signal, ensure that we are not applying any FM signal. Now first we should ensure that the applied carrier signal should be first captured and then it should be there in the lock range. Now how to see the capture range and all those lock range? So we know that, so once we are through with the carrier frequency, free running frequency of this oscillator, you can just measure what is the free running frequency of this oscillator. So once we know that one, we should keep the carrier frequency of the FM signal, which is unmodulated, around that frequency. So when I slightly vary this frequency, if it is there in that range, you can see the carrier frequency also changes. So you can see now I'm increasing the carrier frequency. You can see your output frequency of your VCU is also keep increasing. Can you make out that? Okay, you can see it is keep increasing. So as long as it is there in the lock range, so even if I increase the frequency from 48 to 72, it is still locked. If I further increase, what will happen? So there is a certain range for PLL to just lock to that particular input frequency. If you are there in that range, it operates well. Otherwise, you can see if you further increase, now it is get unlocked. Now the carrier frequency is totally different, and you can see this is your output frequency, this is the input frequency. Those two are totally different. Now because it is out of lock range, you can see now this is totally different. This frequency is very high, whereas this is a low frequency. So those two are not tracking now. So let us again lock it now. You reduce the frequency. Now you can see still it is not locked. This frequency is totally different from this one. So we just keep on reducing. So once it get captured, so we can just make out. Now I can see it is captured. Now if I vary this frequency, that's my VCO frequencies also keep changing. So there is a lower range also. If I just go down 48K also, you can see it is, now it is, you can see now this is locked. If I go anything less than this, it is going unlocked. Now I can see now this is different frequency, this is different frequency. If you operate your FM demodulation with these different frequencies, we will not get the demodulation. We should ensure that the carrier frequency is in the lock range of the PLL, somewhere here. So this is the carrier frequency at which I can apply now my FM signal. So let us apply the FM signal. Okay, you can see in the previous case my carrier signal was a square wave. Of course it is true for either sine wave or square wave, your PLL is going to lock. Even if I apply a sine wave, you can see it is still locking. You can see it is still locking. Now let my carrier shape will be sine wave. Now let me apply the modulating signal so that I get the FM signal. Now let me apply some. Now you can make out there is a change in the carrier frequency because I applied the FM signal. That is reflected in your variation of the VCO frequency also. So once we are getting this type of variation in your carrier frequency as well as the FM modulated signal, then we can say that our PLL is totally operating in the lock range. Now this is to ensure that okay, your PLL is locked. So once you are through with this waveform, we can go to pin number 7, where pin number 7 is a demodulated output. If you see at the output of this, now this RF and CF will constitute a filter. So we'll see at this point what the waveform just after RF at pin number 7. So this is the point which corresponds to RF and pin number 7. Pin number 7 happens to be this. So this is RF. After that capacitor, this is after that filter. Before I amplify the signal. Now we know that the modulating signal is in terms of millisecond. I can see we are already through with the demodulation. But the problem with this is we are having some ripple, as well as the amplitude is in terms of 0.2 volts. So it is of reduced amplitude. But we can say that this is a demodulated waveform. Let me vary the frequency of my modulating signal. You can see that frequency, that output frequency also changes. So that means to say whatever waveform that we are getting at the output of that PLL is a demodulated waveform. So let us still improve that waveform by passing it through a amplifier which has got a gain of around 100. So this is again an amplifier of gain 100, and we got one more filter to remove the ripple. So let us see at the output of amplifier and the ripple. Now this pin number 6 happens to be the output of the amplifier. You can see the output amplitude has been increased. So let me slightly reduce the. You can see the amplitude is, it was earlier in terms of 0.1, 0.2, now it has been increased. Now I can see there is some ripple over there. I can still remove the ripple by filtering out the waveform by passing through one more filter. That happens to be this. So this is my final output waveform. Let me just compare this with the modulating signal. So my modulating signal happens to be that we can get it from you can see both are having same frequency. So this was my original modulating signal. This is frequency modulated and then demodulated version. So this is the demodulated waveform. You can see the frequencies are 100% matching. The frequency of your demodulated waveform and the modulating waveform are certainly matching. There is a slight phase shift because it has to pass through the filter. So the main thing in this experiment is that we should always keep the carrier frequency. First we need to capture it, and then we should keep the carrier frequency in the lock range. Then you apply the modulating signal. You first verify what is the waveform at pin number 7. So once you are there at pin number 7, just after that RF, you will be having a demodulated waveform of lesser amplitude. Then you just amplify it through this op amp circuit, and then you can see the output of the filter, which is a better waveform. So this is how we can do the FM demodulation.